In this video, we're going to look at calculating the critical points and the absolute extrema for a two-dimensional problem. Now, this is not related to the d-test for critical points. We don't have to determine from sort of those higher order derivatives what the behavior is going to be, because we're going to be looking at a closed boundary, a closed region. And so we're going to be testing actual values, actual numbers into the function to determine which point is actually the largest and which is the smallest, because you might have a maximum, say, in the middle, but there might be a point on the boundary which is higher. So we are going to find critical points, but we're going to have to do it in several layers because we're going to have to find critical points in the interior. We're going to have to find critical points on the boundaries, and then we're also going to have to test corner points. Now, this is an extension of absolute extrema from the one-dimensional case, but because the boundary is more complicated, the process that we have to follow to find those potential points that we need to check is also more complicated. Now, as with some other cases with the two dimensions, we're only going to look at the two dimensions, but we can extend this beyond the two dimensions in principle, although, of course, if you add additional variables, then you add additional layers of things that you have to worry about. So we're just going to look at the two variable case. Now we have this function 3x squared plus 2y squared minus 4y. And in addition to that function, we have restricted it to a particular region. In this case, y is greater than x squared, so above this parabola, but less than 4y. Now, the first thing that we're going to do is going to be similar to what we would do if this was a relative extrema. We're going to find any critical points on the whole surface, and then we're going to see if they fall inside our region. As with critical points in the one-dimensional case, if they fall outside our region, we throw them away. So we're going to take our first derivative. The derivative of this with respect to x is 6x, so x is 0. We're going to find the derivative for y, which is 4y minus 4. And so we get we'll set this equal to 0. We get y equals 1. Now, that point is going to be right here, which is inside the region. And so we keep it. So essentially, one way of sort of keeping track of these things, off to the side, build a table with all the critical points that you have to check, all the potential boundary places. So our first critical point goes at the top of our table. Now we need to test, and this is part of what's new, we need to test the boundaries. But the boundaries are not just like individual points like they are on a one-dimensional interval. They're actual functions. And so we're going to test what happens to our region on each of the boundary lines. So our first boundary line is y equals 4. And so I'm going to plug that into my equation to reduce this to a one variable case. What is the behavior of the function that's hovering over this region on that boundary? And it essentially is going to behave like 3x squared plus 16. We're going to take the derivative, we're going to set it equal to 0, and we're going to find out it has a critical point at x equals 0. So since we had already set y equal to 4, 0, 4 is another point. It's going to be right here. And again, you can kind of think of this 3x squared plus 16. It's going to look like an upward facing parabola. And its critical point is going to be right here at x equals 0. So again, that's going to go in our table of things to check. The second boundary we had was y equals x squared. And so we're going to replace y with x squared, turn this into a one variable equation. And when we do all of that simplifying with the algebra, we end up with 2x to the 4th minus x squared. Now, we're going to take the derivative of that, and we're going to find out any critical points that are on this curve. And when we do that, we get potentially x is 0. That would be a critical point at 0, 0. So that goes in our table. But then also 4x squared minus 1 could be 0. So that would give us plus and minus a half. And we plug that into the y equals x squared in order to get 1/2 and 1/4 and negative 1/2 and 1/4. So 1/2 and 1. So there's going to be something going on maybe here and something going on here. And we've also added this 0, 0 down here. And then the last piece that we have to consider is any intersections on the boundaries, because those could be like the endpoints of our interval, they could be maxima or minima, but they're not critical points overall, but they are corner points of our boundaries. And so these intersections right here and here would also go into our table. So we have a list of points to check. We got 1 point from the first critical point of the whole function. Then we got a second critical point from this top boundary, which was right here. We got 3 critical points from the x squared boundary. So now we're up to 5. And then we had 2 additional critical points from the intersections. So we end up with 7 points to check. This is very common for these absolute extrema problems. It's not just checking 2 or 3 or maybe 4 points. It's checking 5, 8, 10 points on a regular basis. But at this point, we just plug them into the original function and we find out what the value of the surface is. So if I plug in my first one, 0, 1, I end up with -2. If I plug in 0, 4, that's from the y equals 4 boundary, I get 16. If I plug in 0, 0, I get 0. If I plug in 1/2, 1/4, I get -1/8. Negative 1/2, 1/4, I also get -1/8. If I plug in 2, 4, I get 28. And -2, 4, I also get 28. Now, I'm going to then choose which of these is the smallest and which of these is the largest to be my absolute minimum and my absolute maximum. So the smallest of these values is at -2. It is the actual critical point of the surface. So that is my minimum on the region. Again, the absolute minimum on the region. And then my absolute maximum is going to occur at these 2 corner points in this case. I list both of them because they both have the same z value. And so those are my absolute maxima. So I have 3 absolute extrema in this case.